Okay, so now we're looking at neurons. So at the end of an axon, neurotransmitters are released and they travel across a gap of width L to get to the receiving cell. So it says we can model each neurotransmitter as a sphere with a diameter of 0.8 nanometers. We can assume the viscosity of the fluid within the synapse is eta equals this number. And they want us to estimate the diffusion constant of the neurotransmitters. And they tell us to use Kb equals something, and it's always equal to that, and we're using a temperature of 310 Kelvin. Okay, so these little particles are diffusing across this gap. So let's look at what we have for diffusion. Okay, so they told us kBt and they told us temperature. So out of all of these equations, this one's looking good, right? So let's try that. So we're looking for the diffusion constant D, which is kBt divided by 6 pi times viscosity times the radius. And remember this is the drag force on a sphere. And we're talking about modeling these as little tiny spheres. So we have Kb, we have the temperature, we have the viscosity, and the radius is 0.4 nanometers. So if you plug in all those numbers, you just get 7.2 times 10 to the minus 10th meters squared per second. Okay, so under passive diffusion, upon release from the axon, it takes 0.002 seconds for the neurotransmitter to reach the receptors in the receiving cell. Given this, how long must the distance L between the axon and the receiving cell be? You can assume 1D diffusion, since you're only concerned with diffusion in the x direction across the gap. So it's hinting at us to use diffusion in one dimension. So if we look at our equations for Brownian motion and diffusion, we see that the mean squared displacement in 1D is 2 times the diffusion constant times the time. The mean squared displacement is 2 times d times t. And we want to know the distance L if this is the time t. So the length scale here is buried in this. So this is the average displacement squared, but we just want a length. So our L should be the square root of this average position squared. So if we substitute numbers in for that, we'll just get, and we found D in part A, get 1.7 times 10 to the minus 6th meters.